Is that better? Yes. Want to start by thanking the organizers for the very nice opportunity to be here. It's really an honor and a pleasure, and to have the opportunity to tell you a little bit of my view of why molecules are so exciting for quantum simulation and sensing. So, and hopefully I accomplished that. So before I start, this is the most important slide, so I want to have it first. I want to acknowledge all the collaborations that I have. So most of the work that I'm going to tell you today has been through many, many years of collaboration with the KRB group at JILA, Junji, and there is fantastic group of graduate students and postdocs for many generations, and I think Tim is here representing the group. And of course, a very nice and productive collaboration with many theories. And I think these are postdocs, graduate students, but also you will see very nice faces here that you will identify. And although I try to squeeze a little bit of on this talk of the collaborations with Conquenni on sodium cesium, I don't think I have time. Well, maybe a little bit is in the questions. And I know that Lawrence gave a very nice highlight, although very preliminary, of the work that we are doing on calcium fluoride. So, but I just want to say this is very exciting times. So, and for this talk, I decided also to make an overview of the path that we have go through the achievement of ultra-cold polar molecules. And the interesting part is that I'm very fortunately, because I think one of the starting points was exactly when I was joining JILA. And it was an effort that was at the beginning very JILA-centric, but the exciting part is that it's not longer that way. But anyway, I mean, in 2008, I think it was when it was the first biggest step toward ultra-cold polar molecules, when June and Debbie and a fantastic group of postdocs and graduate students, you can see here the picture of Conquenni, were able to create a high space phase space density of KRB polar molecules by associating the atoms, ultra-cold atoms, into a stirrup and really start enriching and preparing a gas of raw vibrational ground states. With the big surprise, or not necessarily surprise, but with the big finding that unfortunately, even in the raw vibrational ground state, the molecules were not super stable, and instead they decay very quickly due to chemical reactions. So this was, on one hand, well, disappointing, but on the other hand, it opened great opportunities for even theories start to jump in and try to tell the experimentalists how to save the run. And in particular, the idea that polar molecules, when have interactions that are anisotropic, and the ones that are head side by side, are repulsive and good, but the fact that the head to tail are the ones that are attractive, that lead to the chemical reaction, was the one that we needed to suppress. And then a lot of theory work trying to understand and control these chemical reactions. There are a few faces and names here. And well, maybe you can see here also Daniel Yun here trying to help for the control. And the idea that actually it's possible, and you are going to actually extend the lifetime from milliseconds all the way to 25 seconds by trapping the molecules in the appropriate geometry, going from pancakes to one arrays of 1D tubes, all the way to at least the 3D lattice, when the molecules are frozen, not moving, and therefore you really have mostly the lifetime of the full lifetime up to light scattering. And this is where the idea of preparing a long-lived gas of polar molecules for the exploration of magnetism came to life. And this is where theories like me were really, really happy. I mean, the feeling was low, is very, and keep being low, but anyway, we were opening the possibility to actually explore magnetism in the system. And well, the idea was simple. So even though at that time there was already beautiful theory work trying to explore all the properties of relatively complex molecules, we went in the simplistic path of Bialkali first and say, well, maybe what we wanted to do is really consider just the rotational levels. Of course, even in the Bialkali, we have hyperfine levels, but we were focusing, let's try to see in the regime a strong magnetic field where these hyperfine levels are decoupled, and we can really just think about the rotational levels in the molecule. And in the presence of an electric field, we should be able to really control and isolate two levels, and even use the fact that these two levels uh, um, have a dipole moment that changes as a function of the electric field, not only the transition dipole moment, but also the permanent dipole moment in these dress rotational levels, then allows to really select two specific levels to implement an effective spin 1/2 and go from there. Um, I don't have time to tell you a little bit about going beyond that, but maybe Timur, he's going to tell you in his talk about the possibility to expand the control of the rotational by mixing them with the hyperfine, and actually have more degrees and tunability, but you need to start decreasing the magnetic field. So here B is just the rotational constant. In this case, that is the order of gigahertz. Okay, so, and I just wanted to present you for me is the dipolar complex, because this is something that is really excited, that is just starting to be explored. So one important point to emphasize is that when we use rotational levels, the splitting is of the order of gigahertz, and therefore the wavelength of the transitions that we are talking about is of the order of few centimeters, compared to the spacing that we typically trap the molecules, that is of the order of micrometers less. Then we are in the very strong near field limit, where the only interactions that we worry about are the 1/r³ interactions, that we have to not worry about super radiance or anything else. So the dipole-dipole interactions terms are reduced to this form, and even though it's not explicit here, I want to write these interactions in the form of a sum over a different type of angular momentum projections over the product of two tensors. One is associated with the angular part, the angular momentum, the external degrees of freedom. That is, if we have two molecules joined by a vector r, then the angle that describes these vectors respect to the electric field, for example, that says the quantization axis, is what sets the components of this spherical harmonic. And the another two rank 2 tensor that is made by the two dipoles that involved in the interactions. So the point is that when we start to expand this term and we try to look at the different components, the Q equal to 0, that is the simplest one that is present, the only present when you have only two levels, is the one that we are very familiar with, that they have the characteristic Q equal to 0 spherical harmonic, that is 1 minus 3 cos squared theta. And then you have these dipolar components that, as you can see, preserve the projection of the dipole moment and the angular momentum, each one separately. So this is 0, 0, and then this is the 0 component. But something that I wanted to bring up is that this is only the first step. And even back in 2014 or 2000, I mean, a few years back, we were very excited about the possibility to explore even more terms. So if you are going to have not only two levels, but imagine that I isolate the n equal to 0 state and just work on these two excited states in the n equal to 1 manifold and the 0 level, you can have transitions where a molecule goes down and the other goes up. So these are the Q plus minus 2 terms that have a very different geometrical structure that can give rise to chirality and very exciting directions. I think Sebastian is already seeing those terms, but we were exploring these terms and we predicted that you are going to have, even in frozen molecules, manifestations of some spin currents that have angular momentum and emulate what we call, bilayer graphene, and has quasi-particles that we term as chirons. So it's exactly that maybe we're starting to explore this type of opportunities. And moreover, okay, this also overlap with the Einstein-Dehaze effect that was predicted also for mobile particles, but it can manifest even already in frozen molecules. And if we go one step ahead in the complex, we are going to have, for example, all these three levels. We can build models of condensed matter like wild semimetals that could be very interesting to realize. And there are a lot of potential. So this is just wanted to say that we are just starting to explore all these very rich complex. And well, and now I'm going to focus in the case of q equal to 0. This is the simplest one, where I can obtain just by isolating two levels, in this case 0, 0, and 1, 0. And if you look at these terms and the q equal to 0 term, because of selection rules, then only the CC term is the ones that connects these two terms, these two levels. And the idea is that you just, because you have the dipole Hamiltonian, you are going to just project this dipole Hamiltonian into these two accessible levels, and then you can rewrite it now in terms of spin operators. So that was the basic idea. So if you rewrite the DC-DC term, the one of the terms that appears are terms that are going to flip the internal, the qubit of the molecule. So, oh Jesus, I don't know what is happening, but okay, if you have these two molecules, then you're going to have terms that are going to flip the exchange, the molecules. This is the flip-flop term that is has the form of exchange interactions, this term here. And proportional to the transition dipole moment, so it's active even at zero electric field. But this is not the end of the story. There are more terms. So we are going to have the diagonal terms. So these are the terms that are that are going to couple to the a C type of the operation, or of the system, or the density interactions. And even though, well, you can see that you can rewrite them as that. We rewrite them in terms of spin density, and spin density operators, and depending on, and they yours this term, for example, terms the energy difference between being aligned and anti-aligned, and is proportional in the difference in dipole moment square. The B term is proportional to the sum of the Abélard's dipole moment square, and then the W term is proportional to the difference in the square of the dipole moments. So just rewriting the equations like that. But interestingly, this, in the presence of tunneling, for example, if you allow the particles to hop, then it can be, we call this model TJBW model, inspired by what is called TJ models in condensed matter physics, where you have electrons hopping in a crystal that have a strong repulsion, and the only terms that matter is the tunneling and the exchange. But in condensed matter systems, the tunneling has to be always larger than the exchange. But in this case, we are opening a path where actually we can be the other way around. There is no constraint on what is the strength of these terms. And actually, back in 2011, we were saying, well, if you can reach these conditions and the generality of the model, we should be able to see superfluidity, D-wave superfluidity, P-wave superfluidity are much favorable conditions. And well, we explored all the details of this type of models that are now starting to be implemented. Okay, but the first task was trying to understand this model, even in the case where molecules are frozen. If molecules don't tunnel, then this becomes a constant of motion, and we only worry about these terms that form what is called an XSZ spin model. So first manifestation of this spin model were explored way back in 2014, where we were doing some type of Ramsey protocol with an echo pulse in the middle, just to suppress the undesired decoherence, and you were prepare the molecules along the X direction in the two rotational states block sphere. Then we let it evolve, and then we measure the projection of the collective spin, that is a projection of the collective magnetization as a function of time, and we see this oscillation and decay that depends on the number of molecules. So basically the oscillations were consistent with these flip-flop terms, because we have a very low filling, so molecules were only most relevant process were of very closely nearest neighbor molecules that flip-flop at that rate, and the decay was consistent, in fact, with the 1 over n decay that we expect from 1 over r cube interactions. So when you see these curves, something that I wanted to highlight is the complexity of the experiment. Even for very dilute systems, we have a 3D lattice, 10 to the 4 molecules. Solving this model is really hard with numerical methods. So at that time, we developed what is called the mobile average cluster expansion that allows us to tackle these problems and have a very good solution. just taking advantage of the diluteness of the system. So this doesn't look so dilute, but the idea is that if I want to compute a collective observable, that is the sum of the single particle observable of different molecules, then what I have to do is that, because I cannot solve the full system, I just focus in looking at the calculation of a molecule I, specific molecule. For example, I'm going to here look at the black molecule. I'm going to do a cluster that only includes for example, in this case, the four closest molecules next to it that are the ones that are contribute mostly to the dynamics. I ignore the others because they're far away and not weak coupling. And then the important part is that for other molecule, I change the cluster. This is very important for convergence. And when we did all these type of calculations for over different clusters, we were able to compare and reproduce the experimental observation. That was nice. But even at that time, the challenges were that we didn't have control of the electric field. The filling fraction was very low, and we didn't have control of geometry. And well, the interesting part is that after 2014, there has been an exponential growth of progress in experiments trying to deal polar molecules. So we have the possibility of actually control the nuclear levels of the molecules and see very long coherence time at MIT. Then the preparation of a Fermi degenerate gas, not only at JILA, but also in Munich. The possibility to actually do dipolar system evaporation in 2D in JILA and Munich. And then opening up to single particle control. That's so beautiful when we are going to have twisters or quantum gas microscopes. And here, for example, I highlight Lawrence experiment that were able to see the same oscillations, but targeting specific molecules in the array because they have a single particle, they can have a single particle resolution, and similar experiments in Princeton done by Wasim. So very, very nice control. And also then we are starting to have control of the electric field and shielding, microwave control that open new paths, the possibility to have layer selectivity, controlling geometry, all the way what we are here, where we have implementation of TJ models, flow key engineering, have fidelity gates, a molecular BC now in Colombia and Hong Kong. So exciting. So just try to emphasize in the talk that this is just a few of the reference, but there is really great opportunities ahead. So very exciting time. So now let's go into focus on the JILA effort. So we were able to, from 2013 to this year, we're able to gain control over geometry, rotational state, and electric field. So you heard very nice progress by team. So the possibility to isolate different layers in the molecules and work with one or three has been very useful, and the possibility to extend the control not only from equal to zero electric field, to all the different values as going to explain. So one of the first steps that we were very excited about is the fact that they can isolate the molecules in a single pancake. So then even the molecules are so weakly populated, the filling is low, if you let the molecules move, then still you can have rich physics. So that's one of the first focus that we had. And the idea is that, well, maybe if we have a system that is still dilute in these 2D pancakes, we can operate in what we call the collisionless regime, where the harmonic oscillator levels, that are the single particle levels that describe the physics of these fermionic particles in the trap, were highly spaced compared to the dipolar interactions in the system. And in these conditions, if the interactions are weak compared to that, then collisions that change the mode are going to be suppressed, and because they cause energy. So the dominant type of collisions that happens are the ones that keep the motion fixed, but the only thing that change is the spin degree of freedom. So that's beneficial for many reasons. First, for theories, it allows to write now a spin model, not in a position lattice, but in an energy lattice, which facilitates long connectivity, because if the particles are mobile, instead of having the 1 over r cube coupling, that's the histogram of the couplings if you are frozen, because they are talking to each other, that the couplings becomes very long range, and you can see the histogram reduces significantly, meaning that you have mostly all-to-all interactions. So what is the advantage? So in this case, we can rewrite the model now again, a spin model, forget about the motion in the modeling of the system. It's again an XXZ model with renormalized coupling constant that are now projection on these harmonic oscillator states. But because the couplings are really all to all, to an excellent approximation, we can simplify this model to put the couplings aside, put the average value, and we have a collective spin model that we can understand much simpler. So these are the average couplings, and I'm rewriting this Hamiltonian at S dot S, that is the SU2 symmetric pair, and the C square, where the C is parameter is proportional to chi, that is the difference between JC and J pair coupling constants. So what is the advantage? That is this S dot S term is very nice because it will help me to protect against decoherence that is hard to avoid in many of the polar molecule experiments, and even trying to avoid undesirable S-wave collisions and chemical reactions. So the idea is that in most of the experiments, besides the dipole-dipole interactions, you do have some inhomogeneities, for example, because of the star shifts, because the two rotational states can feel different trapping frequencies, and this generates like local disorder that is very bad for your coherences. But because this term is present, it opens an energy gap between the S equal to n half that you prepare with the poles to the other one where you have a single spin flip because of this decoherence. I mean, this decoherence tries to couple this. But if there is a gap, this coupling is suppressed, and then you keep the coherence longer. And this is our predictions that as you are going to operate the system, in these geometries, you are, even if you have some inhomogeneities in the trapping frequencies, this is, instead of decaying very quickly, you are going to present the coherences as long they are not detrimental. So that's one of the gains. But in addition, this other term that is also present open a path for quantum enhanced metrology. It open a path for spin squeezing, because this is the holy grail Hamiltonian that people want to engineer, for example, in optical cavities. The idea is that we can start looking at this. This was a Bloch sphere, but at the mean field level, this term already can have very interesting consequences, because at the mean field level, this term means that you have an effective magnetic field, or that is proportional to the collective magnetization of the gas. And this, our prediction is that this could be explored. And interestingly, it was seen in the experiment. So when the experiment prepared a 2D layer and added some type of SYA pulses to suppress further decoherence, what the mean field prediction was that if you are going to see the perception of the collective Bloch vector is going to precess in the presence of this external magnetic field that is generated by the other molecules in the array, that was going to set by the collective SC, that is going to be set when you actually prepare the molecules with the first Ramsey pulse. It was going to be proportional to the density, and this chi effective, that is the difference between JC and J perp. And in fact, the experiment confirmed all these predictions. So as they increase the filling fraction, the slope of the phase that you accumulate, or this precession, this density shift increases. The density shift change as expected, depending of the electric field value, because it changes, it controls the difference in coupling constants. And unfortunately, the part that they didn't see is the stabilization of the coherence. The experiment at longer times, the contrast decay, and that's not consistent with the model that assumes collisional free dynamics. The idea is that, okay, these mode changing collisions start to become important. Nevertheless, I wanted to say that the validity of this mean field model at short times was further validated in recent experiments when they add flockade engineering and access different type of Hamiltonians. But at that time, it was clear that if we wanted to keep coherences, you needed a lattice, at least at these current conditions. And that's the next of experiment, when they add a lattice and control of the, well, besides SYA pulses to control the coherence, they added a lattice and were able to operate not only in the 3D geometry, but create a corrugation along the different pancakes, and even go back to an array of tubes with a 1D lattice at which they tuned. And this is when open a path for the first implementation of the TJBW model in the experiment, by varying the lattice geometry from different lattice depth, controlling the electric field, and, well, the filling fraction remain low. I mean, not high, but still we can see the effect of the motion. And one of the parts is that theories we will challenge again, because in the presence of motion, the maze that we had was not valid. So what we had to do is that we have to now work in what we call a generalized mobile Abel cluster expansion, where we have to increase the size of the cluster, because if the molecules move, then we have to account for the motion. So instead of very small clusters, we have to go to bigger clusters that become very heavily on the theoretical side, because we have to diagonalize. But well, with some effort, we were able to extend to some directions. Okay, I have 5 minutes, so and in the no, or no, it's already okay. I'm going to speed up. So sorry. So I just this is just in the deep 3D lattice. We were able to explore the spin model, and we were able to change the J perp and the chi value, and we were able to actually see the manifestation in the spin dynamics. So interesting, the Heisenberg point, when JC is equal to J perp, we see no contrast decay. We characterize decay of the contrast, and we can see that at this point, the contrast doesn't decay at all, or the time, the part that depends on the density, as expected, because you start with an eigenstate of the model. And we were able to reproduce the different values for different exchange model, and the theory and the experiment were in very nice agreement. So go back very quickly, when we allowed the molecules to start moving, well, what we were seeing is that in 1D, when we were just doing tubes, the theoretical predictions of the generalized maze was able to reproduce the experimental dynamics, both at 1 kilovolts per centimeter, and also at much larger electric fields, 12.7 kilovolts per centimeter. We were seeing very good agreement, but the idea is that actually only at the very small electric field, we see a lot of dependence of the contrast respect to the tunneling rate or the lattice depth. So the contrast become worse at shallower lattices. But for the others, the contrast was almost fixed. This is because the method worked very well, because there is an harmonic oscillator still remaining in the trap that localized the particles. Our maze was okay to not, because it was not suffered for great delocalization. But when we were to our GOAFLs and we would let the particles delocalize, there is still some delocalization along the radial direction, and you can see that as we go to shallower lattice, our model completely breaks down. So we were able only to qualitatively capture the decay of the contrast. So for what we can see is that depending for the lowest electric field, as you start to increase the lattice depth, decrease the lattice depth, you can see that the contrast gets worse as in 1D. But interestingly, as you go to shallower lattice, you can start see that the contrast start to get better. So the decay start to decrease. That is very nice, because it's some signatures that in fact motional delocalization could help us, as we were predicting in our energy lattice model. So I'm getting long here, but what I wanted to say is that these ideas I have also seen in magnetic dipoles, when they have trying to explore in Michael Greiner group what is the spin squeezing and contrast experiments. And in fact, for the shallowest lattice, larger tunneling rate, they see perfect preservation of the coherences and almost the emergence of all-to-all interactions. That is very encouraging. And in the case of magnetic atoms, for example, in chromium, in the Bruno Labourte group, they were seeing a preservation of the contrast when you have a BEC, and as long as you go to the mode insulator regime, deeper lattices, the contrast decay. And we were able to actually explain the abrupt jump between the mode insulator and the superfluid by some hydrodynamics equations. And then there is the very nice preliminary experiments in Lawrence group. And just I'm running out of time, but I think there is the possibility to actually explore spin squeezing, and the possibility to reach regimes where the spin squeezing can become collective as a function of the ratio between JC and JPerp, by exploring this type of Heisenberg XYZ models or XXC models. And in this case, the idea is that we should be able to reach, in principle, collective spin squeezing with 1/r³ interactions, as long as you are in 2D. Well, 3D is a little bit possible, but you have to look at the anisotropicity of the dipole-dipole interactions. And well, we can start with expand from just one layer into the two bay layers, and maybe Luis is going to tell us a little bit of exciting physics that you can have, even more complicated forms of squeezing, two-mode squeezing, so that's really nice. And then I'm reaching out my last of my talk, but the possibility of single particle control is amazing. There is the possibility to really start to have very high fidelity gates. And actually what I wanted to tell you about is understand the effect of the temperature on how it impacts the fidelity of the gates that you can do in trap molecules in tweezers. And we think we have very nice understanding. And with that, I mean, we were able to help the group to understand why the fidelity was 0.94. And well, of course, there are very pretty experiments in Simon's group when they were able to reach very high fidelity. I'm sorry, I'm going now, finalize, and just leaving you with a future outlook of, I think there are very exciting vista ahead. So sorry, no, I'm going here. Yes, here, I let you. Thank you for your attention. Sorry to get long.
Thank you very much, Anna Maria. We have time for one or two quick questions. Oh, yes, I have a question actually in terms of the squeezing. I mean, for, I guess, atomic squeezing, we are now finally at a point where the squeezing or entanglement becomes useful really for metrological gains. I mean, this kind of squeezing, I can imagine, okay, it's all, I mean, for an EDM, it would be a Ramsey interferometer, so I could boost this with this.
Yes.
But then many experiments would also be just counting populations, for example. Is that still useful for this? I would have to rotate, right?
I mean, the squeezing. I mean, in the Ramsey interferometer, you always have to rotate and to measure, transfer the coherence into population. But there are more. I mean, if you have the two layers, you are going to have the more generalized S11, SU11 interferometers that are allowing you to measure differential phases. So not only collective phases, but differential phases. So there are different routes of spin squeezing that we can explore depending on the type of measurements that you want to do in the experiment. So I think there is a very exciting direction to explore.
Yes, indeed. Are there any other questions? Otherwise, in the interest of time, then I think we should move on to the next speaker. Thank you very much again, Anna Maria.